there's a light right beside my head. I'll have to pay attention to that another day. Good afternoon, everyone.
Professor, you doing a new setup, man.
Good afternoon. Yes, a new setup. I'm actually in North Carolina right now.
What? Man visiting Joe Rogan?
No. This is where I came from before I moved to St. Croix and live. So, see some friends, vote, and get some administrative stuff done.
Well, that's good,
come
man.
back down, see family as well.
Well, that's good, man. I hope you had a good flight.
Yeah. Oh God, don't get me started on that. The flight wasn't bad. It was just a pain in the butt because I was supposed to fly up Saturday, but the flight sat on the ground for 2.5 hours because one of the engines was malfunctioning and they couldn't fix it. So canceled it. Made us come up on Sunday, and that's part of the reason what screwed up my scheduling on Monday.
Well, you did the right thing. I wouldn't have flying, no plane that the engine failing. Yeah, well, he's there.
Oh yeah, no, I'd definitely much rather have them figure that out while we're on the ground than in the air. Absolutely.
Yeah.
All right. So I got 1 o'clock. I got no daily quiz for y'all today because we got introduced to the idea of eigenvalues. I could create some question, but it'd be weird and pull everywhere, so I just didn't do it. You'll have a daily quiz on Friday, though. Okay. But what we talked about were eigenvalues, right? Eigenvalues, eigenvectors, and eigenspaces. The eigens. Okay. So they all deal with this same equation in that if I take some matrix, multiply it by my vectors in whatever Euclidean space I'm working in, really all it does is it makes a multiple of that vector. So we have that the value lambda is the eigenvalue. You're going to have that the vector x associated with lambda is an eigenvector. And then we also had on top of that the set of all vectors, or all eigenvectors, corresponding, I didn't really get to fit corresponding in, but corresponding to your particular lambda is called an eigenspace. Not the very strict definitions of these, but this is a nice little kind of reminder of what we covered on Friday. So we wanted to find eigenvalues. Once we have eigenvalues, find their eigenvectors. And then once we had eigenvectors, find the eigenspaces, right? And on Friday, whoops, leave it there for a second. But on Friday, we had that example with the matrix 4, right up here, just in the top right. 4, -2, 1, 1. We saw that one eigenvalue for this was 3, right? And we were able to confirm it, and we were able to find that corresponding to 3, one eigenvector would be the vector 2, 1, and we had the eigenspace associated with it would be anything in the span of 2, 1. All right, so that's what we did on Friday. And we said, okay, well, you gave me an eigenvalue, Aaron. How do I find eigenvalues? Right? We made those 5 observations, and to answer that question, the most important one was that we needed to find the determinant of a particular matrix, because we took this system, AX equals lambda x, we subtracted the lambda x over, factor out that vector x, which is why my identity matrix appears. and then said, this is the matrix that I'm considering. And if we want to have a non-trivial null space, we want to have more than one thing, one vector that I can plug in for x, that'll send this to the 0 vector, then I need the determinant of that matrix to be what? What was that fifth property?
0.
Yep, we want it to be 0. So we want that determinant to be 0. Okay. And I hinted at what this becomes, that determinant of this, and it becomes the characteristic equation, that video that you're supposed to watch before coming today. Characteristic. Oh, wow, that's bad. Characteristic equation. I'm going to just do EQ for equation. So the characteristic equation is a pretty simple thing to find because we're confident with determinants. After I get that, you're going to see that it always becomes a polynomial. And then from that polynomial, we use all of that algebra skills, all the stuff that you were taught, that you're going to use later. Well, this is one of the places in which you use it. So that equation that comes from, I don't have room right there, so right here, the determinant of this matrix A minus lambda I, where we just leave lambda as a variable. That's something we want to solve for. But that determinant is the characteristic equation. Okay. So what we do to find eigenvalues is find the roots, find the zeros for the characteristic equation. Then once we have that, we go through the same process that we had on Friday to find out, okay, well then, what are the eigenvectors for that particular matrix? Then once I have the eigenvectors, what does the eigenspace look like? What is the basis for that eigenspace? So what we're going to do is we're going to use that same matrix. We're going to calculate the characteristic equation, and we're going to see where number 3 that we already found to be an eigenvalue appears. And also we're going to find one more. And so we had A was the matrix 4, -2, 1, 1. Our goal is to find all eigenvalues. That's going to be our first thing, find all eigenvalues. So I want to initially figure out what does this matrix A minus lambda I look like? And then once I figure it out, take the determinant of that matrix. So A is at 4, -2, 1, 1. Lambda is a constant that we're going to be solving for. But what does that identity matrix look like for a 2 by 2 matrix?
1, 0, 0, 1.
Yep. 1's along the diagonals, 0's elsewhere. Which means this is the matrix 4, -2, 1, 1. I apply that scalar multiplication on that matrix on the right-hand side. And I see this is lambda, 0, 0, lambda. I subtract those two matrices together, which means I just subtract the corresponding entries. So it's 4 minus lambda, -2, 1, and 1 minus lambda. And what you'll see once we do enough of these problems, we can always kind of shortcut from this idea to what the matrix is going to look like. Because as you can see here, really all we've done is taken all the diagonal elements and subtracted a lambda from. And that's a consequence of that identity matrix appearing in the scalar multiplication. Identity matrix only has non-zero elements on the diagonal. Multiplying it by a lambda, and I'm subtracting matrices. So we're always going to see that nice little dependable behavior for this matrix A minus lambda I. But this is how we get to it. And I know sometimes in the videos he talks about that little shortcut, just jumping from A minus lambda I to right here. Okay, but that's what that matrix is. So that's the matrix that I need to find the determinant of. Find the characteristic equation.
I have a question, Professor.
Go for it.
In the video I was watching, um, when he was finding the determinant. You see how when we find the determinant, we pick a row.
Mm-hmm.
In the video, he picked a column. Can you do that?
Yeah, you can do it. It's all about just the process. A lot of things with matrices you can do. So with row operations, there's also column operations. But since I never really introduced column operations at the very beginning, plus you don't really use them, you can just stick with row operations for most cases. It's just not a process we went through with finding determinants.
Okay. Because when I was doing some of the web work, sometimes we ended up with a value on the first column, then second column. In the first column, second row was 0, and first column, third row was 0. So I would just use the first column because it was a value and then 0 and 0. You could do that, right?
Mm-hmm. Yeah, from what I'm hearing you describe, yeah.
Okay.
Yeah. But thankfully for this one, right, we've got a nice little 2x2 matrix. This one's a little bit easier to calculate the determinant of. So just take 4 minus lambda, multiply it by 1 minus lambda, and then I need to subtract 1, spell mark, there we go, times a negative 2. So what I would do here is then FOIL that left side out. I would end up adding a 2 to it at the very end. We get, let's see if I can fit it down here at the bottom, that our characteristic equation will be lambda squared minus 5 lambda plus 6. So my characteristic equation is lambda squared minus 5 lambda plus 6. And what we've been saying is the roots of this characteristic equation, what makes this determinant equal to 0, are my eigenvalues. So I want to factor that characteristic polynomial, or characteristic equation, which is a nice little quadratic polynomial. So I'm going to stay here just for a moment because I still see some people like Chevy writing. Thank you for turning your camera on, Chevy, so I can actually see and respond to that. But what does that factor into? What does that quadratic factor into? Lambda squared minus 5 lambda plus 6.
You know, I forgot to do the factoring and stuff, but I know we're going to have an X on each side. I'll tell you that.
Well, X isn't my variable here. What is my variable?
I mean, lambda.
Lambda, yeah. So I'd have a lambda on both sides. But I got to think of, go ahead, Khalid. What is it?
Lambda minus 3 and then lambda minus 2.
Yeah. Think of 2 factors of 6. That when I multiply them together, I get a positive 6. And then add them together, I get a negative 5. The 2 are negative 3 and negative 2. So this is what my characteristic equation will factor into. And then I set that equal to 0. And now I got to go to a new slide. So I apologize if someone's still writing. I can come back to it if need be. So we have, I guess, just to recap real quick, determinant of a minus lambda I. We said is lambda squared minus 5 lambda plus 6, which can factor into lambda minus 3, lambda minus 2. And we're setting this equal to 0 because we want that determinant to be equal to 0. We want to find what lambdas make that happen. Well, we have that nice little property. When I multiply 2 things together and they equal 0, at least one of them has to be 0. So then we get either lambda minus 3 is equal to 0 or lambda minus 2 is equal to 0. Well, that tells us then that lambda's got to be 3 or lambda's got to be 2. Thus, my eigenvalues for that matrix A, which is that 4, negative 2, 1, 1, they are, not is, are lambda 1 being 2, lambda 2 being 3. Now, you notice the subscripts there. This is one thing we like to do because we will have multiple lambda values usually. And you don't want to just have a single variable representing multiple values when you're talking about specific eigenvalues. That's why we like to pull in this subscript here. And we always have this usual notation of go from lowest to highest as you can. So take your lowest eigenvalue, let that just have the lowest subscript, to lambda 1. Lambda 2 would be your next lowest, lambda 3 would be your next lowest, and so on. Right? And this also allows us to say then when I'm talking about lambda 1, if I'm trying to talk about lambda as an abstract without having to do some actual calculations, then we have this way of saying, okay, lambda 1, that is actually supposed to be representing 2. Lambda 2 is representing 3, and so on. Okay? But we now have our eigenvalues. And guess what? One of those we had already confirmed. That's what we did on Friday, right? We showed that lambda being 3 is an eigenvalue. We also now have lambda being 2 is also an eigenvalue. So let's investigate lambda being 2. I want to find both the eigenvectors associated with lambda being 2 and the eigenspace. So let's find the eigenvectors. And eigenvalues associated with lambda 2, which is, lambda 1, which is 2. We've already investigated that second eigenvalue when lambda is 3. So let's do on this one. So again, you have to go through this same process of saying, okay, well, my lambda is 2. So I want to find solutions. I'll do this in blue to A times any vector X equal to 2 times that vector. So what vectors can I multiply by this matrix A? That essentially just means I double the vector. And as we said on Friday, it's not easy to solve it in this form. So we go back to that A minus 2I times X equal to 0. And now we have a matrix with a vector of unknowns equal to a vector, 0 vector specifically, that we know. So we can throw this into then an augmented matrix row reduce and figure out what my x's have to look like. Okay. So that's what we're going to do. So I want to figure out what A minus 2I looks like. Well, as we saw from that shortcut, really I just need to go along the diagonals and subtract 2 from everything. I'll write it out, but we'll see that that's what ends up happening. 2 times 1, 0, 0, 1 equal to 4, negative 2, 1, 1 minus 2, 0, 0, 2, which then gives me 2, negative 2, 1, negative 1. So then I throw this into an augmented matrix system because we're trying to solve, again, that A minus 2I times a vector of unknowns equal to my 0 vector. So I plug this in, 2, negative 2, 1, negative 1. Figure out when that's going to be equal to 0. Again, with this assumption that if I let column represent entries, coefficients for the entries in the first entry of my x, the second column represent coefficients for this second entry. But this is a relatively easy matrix to row reduce. What should be my row reduction here? What should be my operations? Because our goal is to get it to that row echelon 4.
Do a half to the top row.
All right, so let's do a half to the top row first. Shorten that arrow, gotta bring it down a little bit so I can have room. So if I take a half to it, I'm gonna get 1, -1, 0. I have 1, -1, 0 still down in that bottom row. So then what is another good row operation? Heard a lot from Allium. Who else wants to chime in? You got it, Nabari. I saw you on mute.
So minus R1.
Yeah. Row 2 minus row 1. I think I heard you say it through the music. But yeah, that's what all we need to do, right? Because they're the same things, that's going to cancel out. And I'm going to see I'm left with 1, -1, 0, 0 equals 2, 0, 0. So I have a row of zeros, which is always our indication that we have a free variable. So either x1 or x2 will be free. And then that first equation tells me that x1 minus x2 has got to be equal to 0. And we could just say x2 is the free variable because it's second row. But then that system tells me, since x2 is free, then now I can always determine x1. Well, it's just got to be whatever x2 is. As long as x1 is whatever x2 is, then I'll be able to satisfy this equation. x1 minus x2, which means I'll be able to satisfy that system that we were looking for. Right? Taking this a minus 2 times I, my eigenvector or eigenvalue being 2, and get the 0 vector at the very end. So then this means that my eigenvectors are anything of the form where both the first and second entry are the same thing. I can use x2 to represent what that entry is. I could use x1. It really doesn't matter because all I'm really saying is I need to take what vector specifically and multiply it by x2. Or you can look at it as what vector am I left over with when I factor out that x2. What will I get, Chevy?
Okay. When you factor out the x2,
Mm-hmm.
oh my God, I can't see.
Like it's in that bottom right corner of the Zoom.
Mm-hmm.
So if I pull out that x2, undo my scalar multiplication, what would I be left with?
Why don't you do that for x2? I don't understand.
Not x2. So I guess spark your memory. We had 2b and b, right, for the other sets of eigenvectors. And we said we could factor out a b, and we were left with 2 times 1, right?
Mm-hmm.
Undo scalar multiplication, we can factor out our scalars here. So down here, right, I'm saying really I have a scalar and the same scalar, whatever that is. We're using the variable x2 just to represent it. And if I pull out x2, what am I left with?
1?
Yeah, good old 1.
Mm-hmm.
Both entries, right? So really, any eigenvector that I have is just taking this vector 1, 1 and multiplying it by a constant. And that constant can be anything. So that constant could be 1, it could be 100, it could be negative pi. I don't really care. That will still give me an eigenvector for this problem.
X1 can be anything, right? Anything you want it to be.
Mm-hmm. Well, in this one, we said x2 to be our free variable, but really which one there's a semantics to it because which one you set to be your free variable, it doesn't matter. Because you'll end up coming to the same conclusion that your eigenvectors are going to look like some constant times the vector 1, 1. So So I'll give you all a second. Give me a thumbs up if you're done writing. So I know I can go to the next slide just to get some summary information. Cool. I can see most people. All right, so again, we're considering A to be 4, -2, 1, 1. We had eigenvalues, which were 3 and 2. Actually, 2. Let me do them the same way I wrote them. We said the first one is 2. Second one was 3. So then consider this eigenvalue in particular, and we said eigenvectors. Would be anything where I just take a constant and multiply them by the vector 1, 1, or any vector where it's the same thing in both the top and the bottom. So 1, 1 would be an eigenvector associated with lambda being 2. 2, 2 would be an eigenvector. Rid of that down there. Whoops. Someone else give me another eigenvector for lambda being 2. Get crazy with it. Whoops, I didn't get it in Nabari.
61, 61.
Yeah, 51, 51. All right, I could also do the negative of that. All right, there's an infinite number of eigenvectors for this eigenvalue lambda 1 being 2. And that's why we like to identify what the eigenspace is, because there are many, many, many more. So that eigenspace, and again, this is for associated with the eigenvalue 2 or the matrix A that we have written here. Well, it's just anything in the span of this vector 1, 1. Anything in the span of that vector 1, 1 will create an eigenvector for this eigenvalue lambda being 2. Okay.
So so that 1, 1 could have been 2, 2, 51, 51.
Yeah, yeah.
The
It
span.
also technically could be the span of 2, 2. Absolutely. Really, it's just, you could use, one of the things about basis, there's many different bases you can find for a space. And when you're only using a single element to generate it, really what your basis is can be anything in your set. But we prefer ones are nice, they're easy to use and mess around with. That's why we would prefer to just write this as a span of 1, 1. But if you wrote the span of 2, 2, or 3, 3, or 51 and 51, you'd be correct as well.
Okay, thank you.
Yeah. Okay, any other questions?
So the span can be anything once it's within those ranges of the eigenvalues. Okay.
You mind repeating that one more time?
The span could be anything once it's within these numbers.
So yes, when we're talking about the span, when we're talking about our eigenspace, it's the span of this vector 1, 1, which normally we would talk about linear combination, but since there's just a single vector, really means only 1, 1, and then any scalar multiple of this. Okay? And then that span creates this eigenspace for this particular eigenvalue in this matrix. And we'll see that eigenspaces and eigenvectors and eigenvalues all just depend on your particular problem. So I do want to give you all one theorem that you see in the videos. This is another reason why we end up wanting to calculate eigenvectors and eigenvalues, is because these eigenvectors end up being linearly independent. And if you have the right conditions, you can end up making them into a basis. Okay? We're not necessarily going to go, at least today, into why they're a basis, but I just wanted to at least put this theorem out there for you and put it in context of at least this problem that we've been discussing so far. So if I just take a few vectors, v1, v2, all the way to, let's just say, vr. I'm just using this because n we usually like to keep for the size of our matrices, so I don't want to use n again. I just want to say r. If these are the eigenvectors of a square matrix, so I'm going to say of an n by n matrix. Again, that's why I didn't use n as my final subscript for that list of vectors. And it's not always talked about or explicitly stated, but we're assuming that the number of eigenvectors that we're talking about is less than or equal to the dimension of this matrix. So of an n by n matrix A that correspond to distinct eigenvalues lambda 1, lambda 2, all the way up to lambda r. So each of those eigenvectors that we stated before are corresponding to a distinct, a unique eigenvalue. Then that set of eigenvectors, that v1 through vr, are linearly independent. So eigenvectors of distinct eigenvalues, different eigenvalues, will always be linearly independent. This is a really, really cool property in that if we try to end up answering basis questions on top of different things, really all we have to do is find more eigenvectors. Okay, well, do you have a question, Eliam?
Can you prove it? Can you show us, like, give us an example?
Yeah, that's planned. So
Okay.
good. Let me get that written. Maybe I can fit it down here at the bottom. Let's try. So consider that last one we had. Let me write it in blue so I can differentiate a little bit. A is equal to 4, -2, 1, 1. And we had two distinct eigenvalues, right? Lambda being 2 and lambda being 3. And we identified what creates our eigenvectors. So an eigenvector for lambda being 2 would be a vector 1, 1, right? That is an eigenvector that corresponds with the eigenvalue lambda being 2. And then an eigenvector for lambda being 3, corresponding with lambda being 3, would be a vector 2, 1. These are two eigenvectors, or they're distinct, the different lambdas. So then I would want to test, okay, are these two linearly independent? So we go through that same process that we've been doing. Take a linear combination of those two vectors, set it equal to my 0 vector. So in this case, it'd be 0, 0. Which then gets me to this system of equations that I can plug in, meaning I would need to row reduce or find the determinant of the following matrix. Because I'd be looking for the solution And then what is the determinant of that matrix 1, 2, 1, 1? What is it going to be? Let me circle it. What is the determinant of this matrix? Because that was,
It's gonna be
-1.
yeah, it'll be -1. So I'll take the diagonals. 1 times 1 is 1. I'll subtract it from my off diagonals, which is 2 times 1. So the determinant of that matrix, 1, 2, 1, 1, is equal to -1, which means it is non-zero, which means that my vectors are what?
linearly independent.
Linearly independent. And you could set this up. We could also choose 2 different eigenvectors. Right? Let's just say I chose, you can get crazy, thanks to Nabari, 51, 51. And someone else give me another eigenvector real quick, where it's the first entry is double the second entry.
2. Wait, no. I want to give you a crazy number like 2 square root of 1.
Well, 2 square root of 1 would be just 2. So
Exactly.
how about we do 2 square root of 2 and square root of 2,
All right. Yeah.
right? So that's fitting that. And if I did this same process, so it'd be 51, 51, 2 square root of 2, square root of 2. So then I throw those into matrix. Oh, I cannot write small. Come on, work with me, please. Here we go. 51, 51, 2 square root of 2, and then square root of 2. I calculate that determinant. So I'm just going to say I'm doing right here because I don't have much room and I'm trying to keep it all on one slide. It'll be 51 times the square root of 2 minus 102 times the square root of 2, which would be -51 times the square root of 2. So its determinant would be -51 times the square root of 2. But again, all I care about is that it is non-zero, meaning that those vectors are what?
Linearly independent.
Yeah, linearly independent. So as long as you have different eigenvalues and find different eigenvectors from the eigenspaces that correspond to those eigenvalues, you're always going to be able to create a linear set of vectors. So what time is it? 1:37. So I want to move to a new example, finding a characteristic equation for 3×3. But any quick questions on this? It's a theorem. It's in the videos. It is important. We're going to probably see it come up later. I wanted to make sure we're talking about now while we're talking about eigenvectors. So any questions? All right. I'm taking silence as a good. Oh, wait.
No questions.
Cool. Yeah, I should just, when I ask that, if you're good, just always give me a thumbs up. It's a habit I'm trying to get y'all to form and some of y'all to form in 241. Let's do it here as well. All right, so let's move on. So in this time, we're going to focus on the matrix A, which is going to be 2, -3, 1, 1, -2, 1, 1, -3, 2. Okay. So in this case, we're wanting to find all eigenvalues. Eigenvectors that correspond to those, and then eigenspaces. And really that last one, eigenvectors and eigenspaces, they kind of work hand in hand because once you have eigenspace, you know all your eigenvectors. And as we've seen up to now, once I have an eigenvector, I can probably find eigenspaces. But as we found out today, the way to get eigenvalues, which is the first thing we should do, because without eigenvalues, we can't find eigenvectors, is to calculate the characteristic equation, which means calculate the determinant of A minus lambda I. And as we saw, essentially just go along the diagonal of whatever matrix you're given, subtract those diagonal entries from lambda, and calculate the determinant. So I'd have a 2 minus lambda, -3, 1, 1, -2 minus lambda, 1, 1, -3, 2 minus lambda. Now you would then work through this, calculate the determinant, you get this nice long cubic polynomial. But for the sake of time, I'm just going to shortcut to the end. And you get that the characteristic equation is the following. Negative lambda times lambda minus 1 quantity squared. So this tells us we have two eigenvalues. What are they? What are the two values of lambda that would make this thing equal to 0?
It's 1 and 1.
Not 1 and 1. 1 is definitely one of them. Oh God, we're saying 1 a lot. That's one value of lambda that will make that equal to 0, absolutely. What else? She's Chevy.
I was gonna say 3, but I'm changing my mind. Hold on.
What
Okay.
about 0 and 2?
Just 0. 0 is the only other one, right? If I was solving this equation, negative lambda times lambda minus 1 squared equal to 0, this means either negative lambda has to be equal to 0 or lambda minus 1 squared has got to be equal to 0. Well, first one tells me that the eigenvalues lambda's got to be 0, right? Second one tells me, well, if I take the square root of both sides, oops, not 1. Well, lambda minus 1 has got to be equal to 0, and the square root of 0 is just 0. You don't have to consider positive or negative because positive 0 and negative 0 are the same thing because 0 has no sign. But then that last one tells me for lambda minus 1 to be equal to 0, lambda's got to be equal to 1. Now there's an important thing here to notice. My factor according to that root, lambda minus 1, how many times do I see that factor appearing?
What say that again?
That factor, lambda minus 1.
Uh-huh.
How many times do I see it appearing in that characteristic equation?
Twice.
Yeah, twice. Remember that squared indicates I'm taking lambda minus 1 and multiplying it twice, right? Yeah, I saw that. Yes, I love that realization, Chevy. Love that. So that's one thing that we want to keep track of. So that second eigenvalue, -1, we have it, but it has multiplicity 2, because we see that factor appearing twice. Okay. This lambda being 0, we can say it has multiplicity 1, but usually if we don't ever say what the multiplicity is, it's again that nice assumption, it's only appearing once. Okay, so we now have the eigenvalues. I can find my eigenvectors. Okay. So which one do y'all want to start with first? Do you want to start with lambda being 0, or do you want to start with lambda being 1?
0.
0. Let's do that. So then I want to find all vectors such that when I take 0, multiply it by the identity, and then multiply it by that vector x, it gets me to my 0 vector. Okay. Well, in this case, if I take 0, the scalar 0, multiply it by anything, this just becomes the zero matrix. Just kind of weird to write, but really, when lambda being 0, I'm just trying to find out when I take my matrix A and multiply it by some unknown vector x. When is that x? What specific values am I going to have to put in there so that the result is 0? We're going to find out there's multiple things that, other than just having a vector of all zeros, that will fit in there. It's because we're just multiplying by a 0 here. 0 multiplying by that 0 is essentially canceling out any information that that subtraction of scalar times the identity will make. So I just plug my matrix A into an augmented matrix with zeros on the right-hand side, row reduce. So this would be 2, -3, 1, 1, -2, 1, and 1, -3, 2, augmented with 0, 0, 0. I would row reduce this, and again, for sake of time, we're not going to do all of the operations, but you get it down to 1, 0, -1, 0, 1, -1, 0, 0, 0, which turns into the system of equations, again, with this idea of x being x1, x2, x3, having 3 entries, because we're dealing with a 3 by 3 matrix. x1 minus x3 being equal to 0, and x2 minus x3 has got to be equal to 0. And x3 is what type of variable?
Free.
Yeah, free variable. Right? And then this also tells me what x1 and x2 have to look like. I'll just write it up here. Tells me that x1 has got to be equal to whatever x3 is. x2 has got to be equal to whatever x3 is, and then x3 can be chosen to be whatever. So my eigenvectors will look like anything of the form this, x3, 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 which is essentially saying every entry has the same value, which means I can factor out that entry x3 in Chevy. What will that leftover vector look like once I factor out the x3?
1.
Yeah, all ones. So my eigenvectors look like anything in this set, or look like anything like this. Take this vector 1, 1, 1, multiply it by anything. So then my eigenspace, I'm just going to try to fit it right here in this bottom right-hand corner. Is just the span of that vector 1, 1, 1. Okay, so this has a pretty familiar ring to it from what we saw last time. We're going to see something cool happens with that second multiplicity. So I'm going to have to move to a new slide. I'll come back to this at the end of class if you need to finish writing stuff down. We're going to look at lambda being 1 next. Okay. So really quickly, for lambda 2 being 1, this means then that we're looking at a minus I times x equal to 0. So I'm just going to take every entry of A and subtract 1 from it. This leaves me with 1, -3, 1, 1, -3, 1, 1, -3, 1. I'm trying to figure out when that's equal to 0. I row reduce this, and hopefully you see the row reduction would be relatively easy for this one because all 3 of those rows are the exact same. So
Professor,
what's up?
You said when you have a multiplicity of 2, you minus what?
So nothing with multiplicity is dealing with the minus.
How do you
keep that in mind when we're dealing with this?
How'd you get this 1, -3, 1 matrix?
So I took A, subtracted 1 times the identity, which is just A minus the identity. So you take your initial matrix, 2, -3, 1, 1, -2, 1, 1, -3, 2. And then you subtract your identity matrix from it.
Got it.
Okay. So we row reduce this. We see we're going to have 2 free variables this time. And specifically, we get that x1 minus 3x2 plus x3 has got to be equal to 0. But then x2 and x3 can be free. So then that tells me x1, I'll write it in blue right above it, needs to be equal to 3 times whatever the second entry is, minus my third entry. Just solving for that x1. So then all of my eigenvectors will look like 3x2 minus x3, x2 and x3. And similar to how we've been doing it before, I want to see, okay, can I view this as a constant times a particular vector, right? To get a good idea of not only what my eigenvector is going to look like, but what's going to span my eigenspace. Well, I see that I have 2 variables now. Each previous example, we've only had 1. But with the 2 variables, I can say, okay, just then separate it to where I have 1 vector that has all my x2s, and then a third vector that has just my x3s. And I do that, I can see it as 3x2, x2, 0, plus negative x3, 0, x3. So I'd have to sit there and look at it for a little bit to figure it out, but that's one good way to break it down, because then I can look at this as x2, some constant times x2, times the vector 3, 1, 0, plus another constant x3 times negative 1, 0, 1. So this is what all of my eigenvectors for this particular eigenvalue lambda 2 being 1 will look like. It's actually a linear combination of 2 vectors, and that's the key. It's always going to be a linear combination of these 2 vectors, 3, 1, 0, negative 1, 0, 1. So then my eigenspace is spanned by 2 vectors this time. 3, 1, 0, and negative 1, 0, 1. I want to remind y'all, what was our multiplicity for this eigenvalue?
0.
It wasn't multiplicity 0. That was another eigenvalue. What was the multiplicity?
Sorry. Isn't this one 1?
Yeah, here, I'll go back.
Okay, now I'm confused.
Good.
2.
Yeah, we had multiplicity 2 for this particular eigenvalue, right?
Okay.
How many vectors were needed to find my eigenspace, to create my eigenspace?
2.
2. Right? These 2 vectors right here form a basis for my eigenspace, because any eigenvector is created from a linear combination of these 2, and they
Professor,
are linearly independent. What's up?
So I see where you're at with the x1 minus x minus 3x2 plus x3 equals 0.
Mm-hmm.
And the x2 is free and the x3 is free. So how would you get, so that means that x1 is equal to 3x2 minus x3, right?
Mm-hmm.
That's how you got this eigenvector right here. How'd you get the 2 eigenvectors here?
Because I needed to split them up to where one vector just considered one of my free variables, and the second one considered just the other. Because I want to looking at these as a linear combination.
Oh, okay. Wait, let me.
If I have them interchanging, I can't do like this idea of pulling a singular scalar multiple out.
And that's when you have a multiplicity of 1, like a multiplicity of 2.
Multiplicity of 2 means I had 2 vectors
Mhm.
creating my eigenspace. Multiplicity of 3 would give you 3. Multiplicity of 4 would give you 4. And so on. So I just want to then put this language in there, and then I can go back to some slides if you're still writing down. So for this matrix A, which was 2, -3, 1, 1, -2, 1, and 1, -3, 2, we had eigenvalue 0. We had eigenvalue of 1 with multiplicity 2. We had our eigenspaces, which also gives us our eigenvectors. Yeah. So 3, 1, 0, -1, 0, 1. You give a little red dot to separate. So what is the dimension? Of the eigenspace corresponding with lambda being 0? What is the dimension of the eigenspace for lambda being 0? Well, how many vectors am I using to
The
generate?
dimension is 1.
Yeah. The dimension here would be 1, because I only need to use 1 vector to create any eigenvector for this particular lambda value. What about for the second one?
2.
Yeah. So the dimension of the eigenspace for lambda 1, whoops, which are 2, oh gosh, that should be a 2 there. Lambda 2 being 0, what is it? Well, in this case, the answer is 2 because I need to use 2 vectors to create any eigenvector. And those 2 eigenvectors, or those 2 things that create it, so 3, 1, 0, -1, 0, and 1, those are my basis for that eigenspace. So I know that the dimension is 2. Okay, so I know I'm already way over time, more than usual. Do I need to go back to a different slide for anyone to finish copying some stuff down? If
No.
not, worst case, you can get it from the recording. All right,
No.
cool. Thank you for telling me. All right, any questions? Oh, Chevy, I see you're muted. What's up?
Can you go back one slide and make sure I got that?
I think that was this one, right?
Yeah.
Cool.
Okay, I'm good now.
Awesome. All right, any questions?
We'll go back to the previous slide.
Yeah. There you go. All right, well, if you got no more questions or don't need any
Yeah,
more
one more
slides,
question.
go for it.
So for this second eigenspace, wouldn't it be x2 equals 1 instead of 0?
Yes. That's what I get for
Okay.
just rushing through. Yes. Let me not write it in blue. There we go. Let me rewrite that while I'm at it. Yep. Thank you, Josh. I mean, I was testing you. I didn't make a mistake.
Yeah, I know.
All right. So if I don't hear more questions, let me go ahead and stop the recording.